Yeah, thanks everyone for staying for the last session. I'm going to be talking about this paper that we wrote about Pareto-optimal non-uniform language generation. And this is a joint work with my advisor, Moses Charikar. So let me just start with a very simple framing of the core generative task that underlies large language models in an entirely assumption-free manner. So there is some unknown target language, and we are given a finite training data set from that language, and we are trying to generate new strings from that language. So for example, the target language could be that of haikus, and we are given some example haikus. We feed that to the language model, and we want the language model to generate a new haiku. In particular, we don't want the model to repeat any of the haikus that it's seen, because then it would just be a parrot model. But we also don't want it to generate invalid haikus, because then it wouldn't have learned anything. So generate new strings from the target language, which are not repeats from the training data. So that's language generation. But more abstractly, this target language is some set of strings over some ground set of, that's the universe. And we are given some n strings from some target language L, and we want to output some string Z, which is from the target language. And stated at this level of generality, this task would, at first glance, appear to be intractable, because we are imposing literally no structural assumptions on the target language. That's some set. We are given some finite subset of it, and we are asking to get our hands on something that's in the complement of that in the set, right? That could literally be anything. So it might appear that this task is hopeless. But what was shown in this kind of milestone work by John Kleinberg and Sandil Mullainathan was that the effectiveness of language models could very well be explained in this very minimalistic bare bones model. So this is a paper called titled Language Generation in the Limit. And I would really encourage everyone to go and watch John's talk on YouTube on this. But here's the setup. So there's a collection of languages, a countable collection of languages, let's say, over some underlying universe U. There's an adversary that comes along and chooses some language from this collection. That's the target language, unknown to the learner. And the adversary starts listing down strings in this language one by one in an online order, in an online fashion, in an order of their choosing. So that's the input to the algorithm. And at every time step that the algorithm looks at a string, the algorithm is supposed to generate a new string. So that's the two-player game that they define. And the success criterion for the algorithm is that no matter what enumeration of this language that the adversary chooses, there is some finite time step t star, such that all strings that the algorithm generates beyond t star are valid. They're in the target language, and they're also new. Okay, so here's a cartoon for this game. There is an adversary. Adversary chooses some language L70 from the collection and starts listing down strings one by one from this language. So there's X1, the algorithm generates Z1. The X2 algorithm generates Z2. This goes on. And then the algorithm would have succeeded if there is some finite time step t star, which could be a function of both the input enumeration as well as the target language that the adversary chose, but that's finite. And starting from t star, every string that the algorithm generates, it's new and it's in the target language. So if that's if that property is satisfied by the algorithm, it has succeeded in this case. Okay, so that's language generation in the limit. And the result that Kleinberg and Mullainathan showed was that no matter what your collection of languages is, if it's a countable collection, then there is an algorithm that always wins at the scale. So that was their result. And like just to drive down the point, like any kind of reasonable language collection that we might think of, like regular languages, context-free languages, all of these language collections are countable. And their result is showing that no matter what the collection of languages is, there's always an algorithm that succeeds at this worst case task. Okay, and it's even more impressive because there's a closely related task which is called the task of language identification in the limit. And for this task of language identification, Mark Gold famously showed that even very simple language collections, this task is not feasible. Okay, so that was Kleinberg and Mullainathan's result. And okay, so where does our work come into this picture? Okay, so I said that the time step T star at which the algorithm can succeed can depend on both the target language as well as the order in which the adversary lists down the strings. But the algorithm that Kleinberg and Mullainathan propose is actually very sensitive to the ordering of the input that's being shown to the learner. And in particular, an adversary can choose to delay the time of success for as long as he likes. Like, there will be a finite time at which the algorithm succeeds, but the adversary can like really choose to delay gratification for as long as he likes. And that seems like a very like pathological kind of property. And it would be nice to like reduce the power that the adversary has in this model. And in particular, it would be nice if this time could just depend on the target language and not on the order in which the strings are being put. So for this, in a follow-up work by Lee, Raman, and Tiwari, there was this definition of non-uniform language generation in the limit, which tried to remedy this pathology. So what is the setup here? It's the same as the language generation in the limit setup, but the success criterion changes. It's a stronger guarantee now. We require that the algorithm succeeds as soon as it sees some T star many strings where T star is only a function of the target language. It's not a function of the order in which the strings are laid out. So as soon as the algorithm sees T star many distinct strings where T star is a function only of the target language, the algorithm succeeds. So in my cartoon, there was the time step T star at which the algorithm was succeeding. If I replace my input with T star other strings from the target language, you still have the property that the algorithm is succeeding at that time. So this is a stronger guarantee than just vanilla generation in the limit. Okay, yeah, we should think of these time steps T star, which are these language-wise dependent quantities, to be a notion of complexity in the collection. So they are measuring like the language-wise complexity, the language-wise complexities of discerning target languages from within the collection. Yeah, and in a follow-up work, we, as well as Lee, Raman, and Tiwari, we showed that we can strengthen Kleinberg and Mullainathan's result and show that every countable collection can also be non-uniformly generated in the limit. So we can achieve the stronger guarantee for every countable collection. Okay, so every countable collection non-uniformly generatable in the limit. So now you might ask, okay, you're assigning a language-wise success time for every language. What is an optimal success time that you could assign every language in the collection? So that's the question that we started with. Like, could we come up with a non-uniform generation algorithm that is like optimal? It assigns the optimal times for every language. So funnily enough, the answer to that question is no, because the algorithm that we gave has the property that it could choose whatever language it likes in the collection and succeed for that language right from the first time step. So like the first language in the collection, the algorithm always succeeds right from the first time step. So in general, you can't ask for like a globally optimal algorithm, because we'll take our algorithm, take some language and put it at the start, and we'll just succeed at it from the first time step. Okay, so what is an appropriate notion of optimality to study in this kind of instance optimal setting for non-uniform generation? So that brings us to this definition of Pareto-optimality. So we say that a non-uniform generation algorithm is Pareto-optimal if for any other algorithm, if there is some language L at which that algorithm has a better generation time, then there must be some other language L prime at which it must be worse than this algorithm. If the algorithm satisfies that property, then it's Pareto-optimal. So like again, in a picture, A is this supposed Pareto-optimal algorithm. If A prime is doing better at some language L than A, then it must be doing worse at some other language L prime. So that's Pareto-optimality. And the question we ask is, can we do Pareto-optimal non-uniform generation for every countable collection? We show something that's almost there. We show that like you can choose an arbitrarily long finite prefix of your collection, and you'll be Pareto-optimal on that prefix. You can choose however long the prefix is. In particular, as a corollary, we get that for every finite collection, you can do Pareto-optimal non-uniform generation. We also more generally identify like a sufficient condition on the collection which allows our algorithm to succeed, but we are not able to show that the condition is necessary. In particular, we find some simple collections for which Pareto-optimality is impossible, and those collections do not satisfy a sufficient condition. but we still don't know if that condition is necessary. So, and yeah, and I want to say that the way that we come up with this Pareto-optimal algorithm is like a generic blueprint that we apply on our previous algorithm. It extends to like more other settings in language generation that people have considered. So it's like this kind of convenient blueprint that we can apply. Okay, so I just want to flash this like main open question. We still don't know whether we can achieve Pareto optimality in general for like what are the collections for which we can do this. So this characterization is open. And I think I'm going to run out of time. So yeah, I'm going to just say that the algorithm is just, you take the collection, the algorithm that we gave before, but you reorder the languages in the collection by doing some kind of insertion sort on the generation times, and then you rerun the algorithm. So it's just a question of like cleverly rearranging the languages in the collection and then applying the same algorithm again. That's the generic blueprint that gets you the algorithm. And I just want to take this moment to advertise this tutorial that we had done on language generation at Colt last year. Anay does a really good job of maintaining this website. It has all the recent papers on language generation, and yeah, it's kind of a cool topic. And yeah, that's all I wanted to say. Thank you.
Okay, so I have one. So as an outsider to the field, it's a little bit hard to track the field because it seems like people keep probing kind of the limit of what can be generated. And the original inspiration by Kleinberg was to say that, okay, LLMs are doing something miraculous. We know they're not doing discrimination. We're not doing identification. They're doing some other kind of thing. This kind of growing body of research, do you think there's something it's missing in terms of capturing? Do you think there's a property of LLM generation that's magical that it's missing, that maybe that the research can go in that direction?
That's a great question. Yeah. So originally, yeah, maybe I'll paraphrase from their work. Like their original motivation was to like not question the design practices that people use for language models, but like to make the point that if we want to think of the essential reason for why coherent generation is possible, you don't even need assumptions. You need like, even in this very simplistic model, you can argue that generation is possible. But like, I don't know, one nice thing about this model is that you can ground empirical phenomena like the hallucination breadth trade-off in this model. So I feel like one nice merit of this model is that like empirical phenomena can be grounded in this model. And yeah, one interesting question going ahead is how do we bridge it, bridge the gap between practice and like this model? Like, is there a way where we can imagine gradient descent in the space of transformer weights in this kind of collection space where we're moving around in the collections? But I don't know, that's like as vague as I said it is.
Yeah, hi everyone. So I'm going to present another work on language generation. This is joint work with Alkis, who's a postdoc at Yale, and Anay, who just started as a postdoc at Stanford. So yeah, as Chirag was nicely saying before, like the whole sort of premise of this line of work is to sort of give a definition and some like theoretical abstraction of like what is the problem that LLMs are trying to solve. And perhaps like the first thing that one can think of is that LLMs take as input like a bunch of data, and then they assign probabilities of like two sequences of words. And what they do is that when they take as input some prompt, conditioned on that prompt, they output strings that have like some high probability. So that's like the starting point from by Kleinberg and Vlanathan. And then what they said, okay, is like, is there an even simpler sort of problem statement we can come up with? So even simply, one can sort of strip away the probabilities and just ask the following, like strip away the probabilities, strip away the prompts, and just say that, okay, we get as input a bunch of strings, and then what we want to do is that we want to produce valid and unseen strings from the language. Is that, so yeah, that's the starting point of this framework. So here, just string is any sequence of symbols, and then as a running example for what a language is, you can think of it as like the set of all C programs. So like the language that represents the C programming language, just like the set of all like correctly formed C programs out there. Okay, so in order to turn that definition into an actual like mathematical framework, Kleinberg and Mulanathan were inspired by the work of Mark Gold, which was called Language and Identification in the Limit. And this is a very nice paper from the 60s that contains very many influential ideas in learning theory. And what Gold was trying to do is trying to design a precise model for what it means to be able to speak English in order to understand theoretically what artificial machines can achieve. And Gold knew back then that it's very hard to write down explicitly all the rules of English language. So this artificial intelligence, no matter what it does, will have to learn these rules implicitly from data. So okay, just to briefly set up the identification game. This is just a two-player game between an adversary and an algorithm. So like as Chirag was explaining before, we have a countable collection of languages. The adversary chooses some target k at the offset of the game. And then in every round, it enumerates the elements of k one by one. Now, once the algorithm sees some element, its goal is to output an index, which should match the index of the target language that the adversary has in mind. So this is the original work back in the 60s, which was sort of formulated by Gold and then fully solved by Nguyen. And the success criterion here is that from some point on, the algorithm figures out exactly the target. Okay. So some interesting aspects of this model is that the algorithm only sees positive examples. It never sees elements outside of K. It's never told whether its guess is correct or not. It receives no feedback whatsoever. And it cannot have query access to the target. This is a very hard problem, and then Gold showed that it's impossible even for regular languages, and Nguyen fully solved that. So inspired by that, Kleinberg and Mulanathan said, let's make the task easier. Let's just ask to merely generate stuff from the target. We don't need to identify it exactly. This is too hard. So the new game that they proposed looks exactly as the previous one, but now the success criterion changes. And the goal of the algorithm is that in every time step, from some finite time step t star onwards, produces strings that belong to the target, and these strings are unseen. Otherwise, otherwise the task is trivial. Okay. So similarly as before, the algorithm never sees negative examples, doesn't get any feedback. And in order to make the setting interesting, all the languages have to be infinite. Otherwise, the adversary will exhaust one of the languages, and the learner will have nothing to generate from, nothing new to generate from. This remarkable result that they showed was that every collection of languages, as long as it's countable, is generatable in the limit. And what drives this positive result is that generation is a much weaker goal than identification. Okay, so the main observation that Kleinberg and Mulanathan had in their original paper is that the generator loses breadth over time. So I haven't exactly defined what breadth is, but pictorially the picture looks as follows. So imagine that the target K is this green set over here. So what happens is that the algorithm starts spitting out stuff from this very large red area. And then as time goes on, it shifts its focus to a smaller and smaller set, eventually reaching within K. But from that point on, it might reduce to a finer and finer subset of it. So at the end of the day, maybe the target language is all the natural numbers. And what their algorithm generates from is some tiny subset of it, the primes. Okay, so the main question that they asked in their work is whether this phenomenon can be avoided, or there's some inherent trade-off between avoiding hallucinations, meaning only outputting stuff within K, and maintaining some notion of breadth. So in this work, they didn't give any formal definitions of what breadth means. So in some prior work, our group and Chirag and Moses Charikar defined a broad set of definitions of breadth. Perhaps two representative ones are the exact breadth, which roughly speaking just asks that the generator can generate whatever is in K. So this is almost the same as identification. And the second, like presumably weaker notion is the so-called approximate breadth, which asks that the generator still lives like strictly within K, but only like misses finitely many elements of K. Yeah, so we can also have like some more abstract ways to define these breadth notions by like some like more abstractly defined properties of the generator, but these are some like two running examples to have in mind. So the main results in our work and like parallel work from Moses and Chirag is that for any countable collection of languages, a generator can achieve exact breadth if and only if this collection is identifiable in the limit. And a generator can achieve approximate breadth if and only if the collection is like almost identifiable. I will not precisely say what these definitions are, but the things to keep in mind are like these definitions are very much inspired by Nguyen's work and the proof, which relies on some sort of diagonalization argument. And so far, like everything that I have been describing and I've been talking about is on an online setting, but there are like some perhaps analogous ways to state the results in a statistical model, and yeah, they sort of extend straightforwardly there. Okay, so like the other aspect that we looked at in our paper is the stability aspect of generation. So like so far we have not placed any constraints on what the generator can output. Like presumably the generator can change its mind after every time step. So the main thing that we wanted to understand is like how does generatability, with or without the requirement of breadth, changes if we require that the generator stabilizes to something. And yeah, the first result that we shown is that even without the requirement of breadth, if we require stability, there exist collections for which we cannot achieve generation in the limit. And so like being able to change its mind infinitely often is like some property that is inherent to generation. And the second result is that if we require stability and breadth, then these two notions that I described before, like approximate breadth and exact breadth, are characterized by the same condition. So stability makes things harder even when we require some type of breadth from the generator. Yeah, so there are a bunch of like interesting follow-up questions. One is like some more fine-grained trade-off between hallucinations and breadth. There's like a bunch of works who have been that have been looking into this thing. The other one is like allowing multiple responses, and Chirag and Moses have some sort of similar set of results when we look at identification with multiple responses. And then like something interesting to understand is what type of feedback is useful. I guess something that our group and the group from Michigan has worked on is what characterizes generation and stable generation in general. We don't have a complete answer to that. And yeah, like as Chirag said before, we have this website that we have put on a tutorial and various other resources. So if you're interested, please check it out.
Okay, good.
Okay, so our next talk is online covering with multiple experts.
No, Thang. So my name is Thang. Thanks, very good. Don't worry. So it's a joint work with my former PhD student, Nico. It's about online covering with multiple experts. So let's start with a motivation example. So time to time I think about this problem. Maybe that happened to you also. So when you go to the supermarket, I choose after shopping, I need to choose a queue to pay, and then there are several queues. I pick one, and I see that the one close to me run faster. I move. That happened to me. And then later on, I see that, oh, the previous queue now much faster. And that happened to me not only once, yeah, and potentially that happened to you. So this, and time to time, to say the truth, I didn't think about this problem at that time. But then, in fact, it's related to a very old algorithmic question that given multiple algorithms, online algorithm, dynamically involved algorithm, which one you need to follow, which one you need to choose? It's a hard question, and people studied for a long time, and still people discuss about the benchmark, how you compare in order to select the best one. And the question is renewed with machine learning. Machine learning counts with prediction. So assume that now you have the same problem, but you have multiple prediction. Can you do something? And that we try to do. And our objective is to introduce a new benchmark for analysis and also provide algorithm for the problem in the benchmark. This is our paper. Okay, so let's see our benchmark. There are two most popular benchmarks. The worst case paradigm benchmark is very popular in algorithm design. And you have another side, the best expert in hindsight, very popular in online learning. And we propose something in between. It's a linear combination of experts. Okay, intuitively, it looks like that. We will go into detail, but intuitively, you have multiple experts that generate a polytope, convex hull of own expert. And we need to find the combination of own expert. And we compare with the best one. Let's see if it makes sense a little bit later. Okay, so a little bit of formula. I know that is the last session. People are a little bit tired, but you can forget things. Assume that you have prediction, and only one assumption is that we assume that as expert or prediction are also online algorithm. Online algorithm, it means that you cannot change your decision. Your solution needs to be monotone. For example, if you pick an item, something right, you cannot say, oh, I changed, I don't pick this, I review back the item. There are some model for that, but assume that as a solution in monotone is a condition of online algorithm. So the benchmark we consider is some objective. Forget it's a linear programming, but the first two lines are some objective, and you need to find combination between all the experts. That combination change over time. You can change the combination over time, but you need to be monotone in your solution, meaning that you need to maintain your algorithm to be an online algorithm. It's a benchmark. And let's compare to other benchmarks so far. As you see, so far, everything is linear. So assume that the objective is linear, then our benchmark called linear combination is the same as the best expert in hindsight. The proof is very simple, but you can imagine that the optimum solution of things in the polytope is happen in the vertex. You see, one expert, the best one. But for non-linear objective, it's not the same. Linear combination is much stronger. Let's consider an example. Consider max span minimization problem. You have n job, you have n machine, and unit job, right, one by one. And you have an expert. The first expert says that you assign all the job to the first machine. Second says that assign own job to the second machine, and so on. The last expert says that you assign own job to the last machine. So what is the best expert? They are all the same. And the load, the maximum load is n. For each one, the load, maximum load is n. And the best expert, n. But what is in linear combination? The linear combination, you just choose each one with probability 1 over n. You assign job in a balanced way. So you see that the linear combination benchmark is much stronger than the best expert in hindsight. And what is our result for 0-1 optimization problem, covering problem? We get log K, O of log K competitive algorithm for this benchmark. And if we consider linear problem where the decision is not 0 or 1, is something else, then it's similar, but we need to pay by some factor, some role, which we call this it is a discrepancy of the expert. It depends if the experts sometimes say something very big and at some moment they change their mind to be something very small. Then we cannot do much. So now you can ask the question that, okay, good. If K is small, number of experts is small, you can get something close to optimal. If K is big and all the experts are bad, what should we do? We allocate to the bad expert. Not very good. But the best way to apply is the following. We work first on the K expert, and then you can take a favorite algorithm or the best worst K. The online algorithm is the best guarantee. And you combine the two one together to get the final solution. You can do that. In this step, you lose log K, and in this step, you lose a constant time. So finally, you get some log K competitive to the best expert, and at the same time, it's a constant competitive to the best online algorithm you know so far. And very quickly about the algorithm things, we optimize some convex program. It's kind of the entropy function. The new thing is that it's a shifted entropy where we shift in the average direction, in the direction which is the average of all the experts. And there is a subtle step where in the constraint we modify the suggestion of the expert. Assumes that all experts tell you, I need to pick one item, and they say that, oh, choose every set to cover this element. It's too much to do. So we can change a little bit the proposal of prediction in order to capture some good thing. And after solving some convex program, we compare with the previous solution and we choose the one which is larger. We did some experiment. Of course, we didn't have every time the best solution. But the good thing is that when we compare with the even offline optimum, we are not very far. And time to time we beat, especially when we have a worse instance for the multiple weight update. Or even in this case where you have all the very bad expert, we have some very reason. Here's the average of expert. It means that the experts are very misleading. You can get some good thing. When we deal with nonlinear, continuous time nonlinear, the function is nice. But when it's a discrete time, we need to add some term because the math work only in this case. So, but personally, I do not really like it. But I always believe there is some beauty behind, and there should be something nicer. Okay, finally, we provide some benchmark and we design algorithm on this benchmark. One very intriguing question is that covering is dual or packing, but when we apply our technique, we cannot find solution for packing. So far, I think that we have an idea why there is some asymmetry between the two models. But one open question is how we can deal with the packing constraint. Okay, thank you.
Okay. I have one question. I was wondering if you consider alternative algorithms, since the delta T in the update looks like an average of the history. And so it seems like maybe a dual averaging or a narrow descent.
Yeah, we didn't think about it. I think we can, there are some average approach that we can clean, but maybe this one, yeah, we didn't think about it.
Let's thank the speaker again. Discriminative feature feedback with general teacher classes, and Omri will give the talk.
Hi everyone, I'm Omri from Ben-Gurion University, and I'll talk today about discriminative feature feedback with general teacher class. So we studied the discriminative feature feedback protocol, which I'll call the DFF throughout the presentation. It's an online learning protocol with the feature explanations to help us distinguish between examples. Previous work studied it for specific model assumption, and we're going to generalize it to a general teacher class. We define a new dimension that characterizes the realizable DFF mistake bound. We show to a conversion from a DFF problem to an online learning problem and vice versa. We show a tight upper bound for the K non-realizable setting. And we show that unlike online learning, the dependence on K is problem specific. So the protocol involves interactions between the learning algorithm and the teacher. So let's assume we build a movie recommendation system. And then a new movie arrived, The Lord of the Rings. So the learning algorithm can predict the label 0 and provide as an explanation the movie Titanic, because the user didn't like the Titanic movie before. But users do like Lord of the Rings. So the teacher will tell the algorithm that is incorrect. And the correct label is actually 1 and a discriminative feature, medieval fantasy world, because that's the feature, because Lord of the Rings has a medieval fantasy world and the Titanic does not. So why is DFF actually interesting? It provides richer feedback than only labels. It helps to convey more knowledge from the teacher. It is closer to human learning because when a human learns something and makes a mistake, it tries to understand why he made the mistake. And the feature here is the explanation for the algorithm why it made the mistake. Explanation can accelerate the learning, and it can remove the dependence of the space dimensionality of the examples. All previous works assumed a component model with M components, and the results are the mistake bounds in the results are only dependent on the number of components. As you can see, they remove the dependence of space dimensionality. So in order to define the dimension, we first start with defining what a teacher class is. So a teacher T is defined over the space, the example space X, a finite label space Y, and the feature space phi, and is a pair L and psi, where L is a labeling function as a hypothesis in online learning, and psi is the feature feedback function that takes two examples with different labels and returns a feature that is satisfied by the first one and isn't satisfied by the second one. A teacher class is a set of such teachers. The realizable setting is that the feedback is consistent with some teacher in the class. And we now want to define the dimension and show that it characterizes the optimal mistake bound in the realizable setting. So to do that, we'll first define what shattered DFF trees. So DFF tree encodes the interactions between the learner and the teacher. The edges are labeled with the learner actions, and the nodes are labeled with the environment actions. The tree also uses a history of labeled examples, because as we said before, the learner needs to provide an explanation when it predicts a label. So at the beginning of the run, the algorithm needs to have a baseline of labeled examples that it can predict. So here, for example, X1 will be the first example in the sequence. The learner will predict Y0 and provide X0 as an explanation. And then the teacher will tell him that actual label is Y1. Phi1 is the distinguishing feature that X1 satisfies and X0 doesn't satisfy. And X2 is the next example in the sequence. As you can see, whenever we go down each level, there are more edges because the algorithm has more labeled examples that it can provide as explanations. each path in the tree is consistent with some teacher in the class, and all paths have the same length. Unlike little stone trees for online learning, because several paths can have the same label but different explanation, then multiple paths can be consistent with the same teacher. Now we can define the DFF dimension. So the DFF dimension for a teacher class T and the history H is the maximum height of a shattered DFF tree that is consistent with them both. And I will show this theorem that in realizable DFF, the optimal mistake bound for the teacher class and the history with a deterministic algorithm is exactly the DFF dimension. To prove the upper bound, we use the SOA DFF algorithm. It is similar to the online learning SOA algorithm, but it needs to take into account future histories and the feature that the teacher can return as explanation. So instead of only maximizing the future DFF dimension, it can also minimize it by choosing which example to return as an explanation. I will talk about the K non-realizable setting. In this setting, the feedback is consistent with a single teacher in the class in all but at most K rounds. We call these rounds exception rounds. And in these rounds, the label, feature, or both can be different from what the true teacher provides. In online learning, the equivalent is up to K incorrect labels. And it was shown that the optimal mistake bound for every hypothesis class is this. And as you can see, it has K and LD under a square root. And it's both upper and lower bound for every hypothesis class. Now we want to see what's the dependence of the optimal mistake bound on K and DFF dimension. So let D be the DFF dimension of the teacher class. So there exists a deterministic algorithm that makes at most K plus 1 D plus K mistakes. And for any algorithm, there exists a teacher class that causes at least K plus 1 D minus K minus 2 mistakes. So as you can see, unlike online learning, in DFF, the dependence on K can be linear, in contrast to square root in online learning. For many classes, the DFF dimension will be smaller than the corresponding little stone dimension of the corresponding online learning problem, in which case the DFF bound can be smaller than the online learning bound. If they are equal, then the mistake bound is as in online learning. But our theorem shows that some classes have theta of KD mistakes. So unlike online learning, K and D alone do not characterize the optimal mistake bound in DFF. Okay, the mistake upper bound idea is using the agnostic SOA DFF algorithm. So this algorithm uses the SOA DFF we saw before for the realizable case. And after D plus 1 mistakes, it restarts it and repeats it indefinitely. The proof idea is that the SOA DFF makes at most D mistakes if there are no exceptions. If D plus 1 mistakes happen, then an exception round must have happened. Since there are at most K exception rounds, it will restart the SOA DFF at most K times. The lower bound idea uses a DN threshold secret sharing scheme. In this scheme, the secret is split into N shares, where any D shares can reconstruct the secret, but fewer than D shares reveal no information. So the teacher class construction is that each feature provided by the teacher is a share of the secret. So the learner must learn D different feedback features from the teacher. But the exception rounds hide which feedback is reliable and which is not. And with this, we can build a class for each algorithm that causes K plus 1D minus K minus 2 mistakes. So to summarize, we defined DFF with general teacher class. We characterized the optimal mistake bound for deterministic realizable setting. We gave a tight upper bound for the K non-realizable setting using K and the DFF dimension. We saw that unlike online learning, those are insufficient to characterize the optimal mistake bound. And with an open problem, which properties control the optimal K-non-realizable mistake bound for any teacher class? Any questions?
Can you tell us a non-trivial example where the little stone dimension is a lot larger than the DFF dimension?
I can give you, so if you have an infinite vector, that's a binary vector that just returns whatever is inside of index I, then in Little Stone, you won't ever find this index, but in DFF, you can just, after the first feature, you'll know what the index is. So the Little Stone dimension is infinite and the DFF dimension is 1.
Hi, everyone. I'm very honored to be closing this conference. So this talk is titled Reward Selection with Noisy Observations. So this is me, Trung, and this is joint work with my lovely co-authors, Kamyar, Aranyak, Alex, and Qian. Yes, so to start this with, I want to give a motivating example. So we started, okay, let's suppose that you're a company G and you want to sell an ad slot. And say that there are N advertisers that compete for this single ad slot on your website. And the aim is to maximize, your aim as the company is to maximize the click-through rate. Let's say like the probability that the user clicks on the ad. Right, so these are the alternatives, the advertisers, and let's say they have their real hidden click-through rates that you don't know. You can only know when you put the ads up on your website. So instead of this, you have a machine learning like predictor that predicts the CTR, the click-through rate of each of these ads. So let's say it predicts that the first ad have a 0.5 rate, like 50% probability of being clicked on. Second ad has an 80% probability. Third has 10%. Fourth has 30%. But okay, predictions alone is not enough. You also know that perhaps like these machine learning predictions have some variance. So let's say like for this example, let's just say the range. So like the first one, maybe the real value lies somewhere between 30% and 70% because the variance is 0.2. For example, the last one, for the third one, because the probability is like 1, the real value can be anywhere between 0 and 1. And your goal is from these two information, you want to select one advertiser, pick it up, and then put it up, and then you get the real reward, real click-through rate as the reward. So at this point, usually I would ask the audience to pick one, but because in the interest of time, I would just like say, let's say that we click on the first person because like his click-through rate is pretty high, predicted one. And then you'll see the real value and see that the real click-through rate is 40%, while the third one has a click-through rate of 60%. So in hindsight, you should have picked the third one, but you picked the first one. So you gain this reward of 0.4, but actually the best reward is 0.6. So to formalize this setup, let's say that there are n hidden random variables, x1 to xn. And for this paper, we have this very strong assumption that these are drawn ID from some unknown distribution G. Let's say also non-negative. And you have a machine learning model with prediction variances x1 to xn, sigma 1 to sigma n, and also predictions y1 to yn. And the assumptions here are that these are known to you. The y's are drawn unbiased from a normal distribution centered at xi with variance sigma I. And let's say that you sort like the variances for without loss of generality. The algorithm chooses an index x, gain reward xi, and the benchmark is against the hindsight optimum. Here I use this notation to denote like the expected value of the maximum of n IID draws from the distribution G, which is exactly like the hindsight optimum here. And we want to have multiplicative guarantees against the hindsight optimum. Right, so some previous work. Surprisingly, the only previous work that is like really related to this model is by Bax et al., who coincidentally like introduced this model. And in this work, they showed the only theoretical result that they showed is that the naive algorithm that just picks the argmax of yi is suboptimal. And we can they showed that by saying that you can gain expected reward by picking by argmax of yi minus c times sigma I. So you discount the value a little bit, but they don't show any formal guarantees for any linear discount algorithm or for the naive algorithm itself. For our contribution, we characterize when there is a constant approximation algorithm, and our characterizations can be summed up as if enough alternatives have small sigma I, then you can gain a good approximation against the hindsight optimum. But we show that even under this regime, previous algorithms proposed by Bax et al. Can be very far from optimal, and in fact, it might perform as bad as picking a random index. So you know that picking a random index, you just gain expected of d as your reward. We show this. On the other hand, we show that a simple algorithm is constant approximation under this regime, where this algorithm is just picking a random pruning ratio between 0 and 1 and select argmax of yi for the boxes with the lowest alpha fraction of the lowest noises. So to start with, we have this simple observation to think how to know why the naive algorithm is bad. So let's just say that all of the predictions are very bad. Let's just say that their standard deviations are infinite. What are the observations here? First, the predicted values yi give no information about xi. So you can't use this to pick a good xi ever. Furthermore, we know that the yi's range here dominates xi's range. So this gives us the lower bounds for the naive algorithm. Let's say that you have n alternatives where all of them have 0 except the last log n alternatives whose standard deviations is infinite. So here, with probability 1 minus 1 over n, the largest yi is among the infinite variance alternatives. Why? Because as long as one of them is positive, a very high probability their value is going to dominate the range of every yi's before that. So this means that under this event, naive achieves expected d approximately expected reward, and you can show that like bounding together at most two expected of d in general. However, like the very simple algorithm of ignoring all of the infinite variance boxes and picking the rest gives you a 1 minus log n over n approximation to the optimum. This gives us like the intuition that a good algorithm here should only exploit the small noise alternatives and ignore the large noise ones. So what is a good algorithm? Let's say that we're in a good regime where, let's define what is small noise first. A subset of alternatives S is small noise if the maximum variance here is small. It's up to the order of like the maximum hindsight optimum in this set divided by square root log n. And this means that roughly the largest noise does not overwhelm the hindsight optimum within this set. So the lemma here is simple. If there exists such a small noise subset of size at least c times n with some constant c, then we can achieve a constant approximation with a asterisk, as I will explain later. And the proof is very simple. Let's just say you pick the maximum y in this subset. You can bound x of that by yi minus expectation of the hindsight optimum in this set, just because of the small noises. By definition, this y is larger than the y of the optimum. And also with high probability, that y is also close to the xi's. So this just means that with another application of this inequality, you have that picking within this subset is good. But what is the asterisk here? Note that this condition, like the condition of the subset needs, if you want to find this subset, you need to know what the distribution is, which we don't. And therefore, the algorithm cannot find the set S. So this is the asterisk I was talking about. And how do we get around this? So let's say that you sort the alternatives such that sigma 1 to sigma n is ordered, and the green alternatives here are the good set. The idea is that you uniformly randomly cut off the small to big noise boundary, and with probability c over 2, the boundary retains between Cn over 2 and Cn small noise alternatives. So therefore, you additionally lose a factor of C over 2, but that's a constant. So this means that this naive with random pruning algorithm gives you a good approximation in this regime. And yeah, this is the theorem. In the interest of time, I will not talk about this additional result that we have, but we show that in particular, we just show that if your distribution is log concave, then there's an even stronger guarantee that you just have to pick an exponentially random small noise boxes in order to work. And for boundary, we give a definition for a large noise subset, which is min of the sigma in this subset is pretty large. This is almost complementary with small noise up to a factor of log n. We show that, well, there exists a common distribution delta, D, such that if there exists a large noise subset of size k, then no algorithm can achieve better than expected of D times this. Well, the proof of the idea is simple. If D is the half normal distribution, then because of the definition, no algorithm can gain sufficient information on the large noise subset, but the small noise subset can only contribute so much. So in conclusion, we almost completely characterize the boundary of constant approximation here. We provide a simple algorithm in a case a good approximation exists, and we showed negative results for previously proposed approaches. For some open questions, the first one is a very important one. It turns out if the algorithm knows the common distribution D, it is pointwise optimal to select argmax of the posterior expectation. This is what we call the clairvoyant algorithm in our paper. And the important open question here is, if we can learn the distribution from the noisy values, then perhaps we can apply this clairvoyant algorithm on the learned distribution to gain a better reward. This is an important open question to us. Some other open questions include time and boundary, consider other benchmarks. So we consider benchmarks against the Einstein optimum, but the benchmark can also be the clairvoyant or the best algorithms, and maybe other arbitrary noise distributions other than Gaussian. And that's the end of my talk. Thank you for staying until the end.
Actually, I just want if you could go back to the model just to understand that whether both the values and the sigmas are generated from the same distribution, or just kind of trying to understand where do the estimates
okay, here it is. From. So xi's are unknown. The sigmas are known, and they're not generated from any distributions. Let's just say these are parameters of your machine learning models. So they're fixed parameters of your machine learning models that does the predictions. The predictions are drawn from this by this
around those.
Yes.
I see, and it's one round.
Yes, it's just exactly one round.
Nice.
So you cannot interact too much.